Hello, my name is Vladimir Chikin. I am a deep learning research engineer in Huawei, and now I would like to present our new approach for mixed-precision quantization of neural networks based on relaxation of smooth regularization and special technique for explicit model size control. Most of well-known state-of-the-art mixed-precision quantization methods use brute force and their computational complexity is high. Some state-of-the-art methods have begun to use gradient descent to better distribution tuning, but they don't have the ability to explicitly set the required compression ratio of the model. In our work, we propose new method for mixed-precision quantization of neural networks, devoid of these shortcomings. In this diagram, you can see the general pipeline of the proposed method. We define smooth surfaces of constant size neural networks for the given architecture, and construct gradient descent algorithm on these surfaces to obtain a network of size specified by user with highest quality. In addition, we construct the family of regularizers with monotone smooth parameterization of number of global minima. Our proposed method works for any network architecture and any deep learning problem, and also allows user to specify the required compression ratio to be achieved exactly. Moreover, this method imposes almost no computational overhead and requires much less computational time compared to narrow architecture search algorithms. We found that there is a class of functions that smoothly depend on the parameter and at each moment have the corresponding number of roots depending on this parameter, which are also minima of these functions. You can see an example of a formula for such function, as well as an example of its graph on this slide. Therefore, using such functions as regularizers, we can train quantized models, which mixed precision bitwidths are tuned during model training. To do this, we should minimize the loss function demonstrated on this slide. Variables t define bitwidths of weights and activations for different quantized layers. If we consider these variables as independent trainable variables, then there are no constraints on layer bitwidths. In particular, bitwidths of all layers can become quite large, and we will not get the required compression ratio. We propose the following technology for compression ratio control. We suggest to use a special parameterization of the bitwidth parameters of the model layers. This parameterization imposes restrictions on the size of the quantized model. To do this, we built a surface of neural networks of the same size in the bitwidth space. As this surface, we use the surface of an ellipsoid, the equation of which is explicitly associated with the expression of the model size. We parameterize the surface of this ellipsoid using latent independent variables that determine the bitwidths of the model layers. We propose to train the quantized model by minimizing loss function from previous slides relative to model parameters, quantization scales, and these latent bitwidth parameters. Thus, we can train quantized models whose mixed precision bitwidths are tuned during model training in a continuous space. Despite the fact that bitwidth parameters change during training, it follows from the definition of the ellipsoid equation that the size of a model is preserved during training. We validate our approach on image classification and image super-resolution tasks and compare it with the main well-known competing methods of mixed precision quantization, as well as with the some well-known fixed precision quantization method. In our work, we show that our proposed approaches reach state-of-the-art results. In this table, you can find the results of applying our method to image classification task on ImageNet dataset for the ResNet 18, ResNet 50, and MobileNet models. As you can see, our proposed method allows us to achieve better quality of quantized models with a higher compression ratio. Thank you for your attention.